Okay, the topic for today, and it's the last new thing we'll learn about this semester, is regression. And this is sort of the sequel to correlation that we talked about last time. Suppose you've determined that there is a linear relationship, either positive or negative, between the two variables you've been investigating. The next step would be, how do you come up with a formula or an equation that describes what that relationship is, so that then you could use that equation to predict some other values of y that go with other values of x, some other data points that would also fit the same pattern. If your correlation coefficient turned out to be exactly either positive or -1, that would mean that all your data points lined up perfectly in a straight line. And in that case, you could just use algebra to find an equation for the line that passed through all the points. And then you could use that equation to predict other points on the line, what y would go with any value of x. If r was close enough to 0 and far enough away from either 1 or -1, that you said there was no significant relationship between x and y, then there would be no point in trying to come up with an equation or a formula, because in that case, knowing a value of x tells you nothing about what y might be. So there's no way to predict what y would go with any particular value of x. So it would be useless for me to try to come up with an equation that would predict how well somebody would do in statistics class based on the number of letters in their last name, for example. If there's no correlation there, then that's all there is to say about that. But the kind of situation we want to deal with is where there is a significant linear relationship. So you've got data points that maybe don't line up perfectly, but they line up well enough that it looks like there is a correlation, and you want to come up with a formula that you can use that will give you a good guess as to what value of y would go with any particular value of x. That is, what's the equation for the straight line that comes closest to fitting your data points? It's not going to do a perfect job of fitting your data points if the data points don't line up perfectly, but you want to do as good a job as you can. Now remember, if you've studied straight lines and their equations in algebra, you know that the equation for a straight line can be written as y equals, and then on the other side of the equal sign you have an x term and a constant term, like maybe y equals 2x plus 7. In algebra class, you're used to writing y equals mx plus b, with m standing for the number in front of the x and b standing for the constant term. And in that case, m would be the slope of the line and b would be the y-intercept. But in this class, we're going to be writing things a little bit differently. We're going to be writing our equations for a line as y prime equals a plus bx. So we're going to put the constant term first and the x term second, just because that's the way our book does it. And we're using y prime, a y with this little mark by it, instead of just y, because y by itself stands for the actual y value of one of your data points. And y prime in our equation represents the value that the equation predicts. So unless your points line up perfectly, y prime isn't going to be exactly the same as y, but it ought to be pretty close. Now, if you tried all possible values for the a and the b, all possible numbers that could go in there for a and b in y prime equals a plus bx, we would get all possible straight lines. So the question is, out of all those possible straight lines that you could have, which one does the best job of fitting our particular set of data points? Well, the way statisticians do this is they define the best line as the one that does the best job of minimizing the difference between the actual y coordinate of your data point and the y coordinate of the point that's on the line for that x coordinate. So it's how far your actual data point is from a point on the line if you go straight up and down. And then they take all those distances for all of your data points, square each one of them, add up the squares. And they want that sum of that squares to be as small as possible. So that is called the least squares regression line. You don't have to really worry about that, but that's the idea behind what makes this line what it is. It's how this line is defined. And here's the formula for the two numbers that make up that line, the A and the B. So two more big ugly formulas. They're not quite as bad as the formula we saw last time for R, but they still have a lot of those sigmas in them. So again, you can do this calculation yourself, or there are ways of getting calculators and computers and statistics software to come up with this for you. So in one of the examples we were looking at last time, the one about the relationship between the temperature and the number of calls to an emergency service. Here was our data with what the x's and the y's added up to, and then also the sum of x times y and x squared and y squared. So if we were going to use this to calculate the A and the B to get our least squares regression line for this set of data, here's how that would work. To calculate A, we would take the sum of y, which is 62, times the sum of x squared, which is 53,219, minus the sum of x, which is 605, times the sum of x times y, which is 5,535. That would be the numerator. The denominator would be n, which is how many data points we have. Here that's 7, times the sum of x squared, which is 53,219, minus the sum of x squared. So that would be 605 squared. And when I put this into the calculator, I'm going to need parentheses around the numerator and around the denominator to make sure everything gets calculated correctly. So here's what that would actually look like when I put it into the calculator. Parenthesis, 62 times 53219, close parentheses. No, not close parentheses yet. We still have to do minus 605 times 5535. Now we close parentheses because we're done with the numerator, divided by, now we open up a set of parentheses for the denominator and type in 7 times 53219 minus 605 squared. Close parentheses, hit enter, and it comes out as negative 7.544 and so on. To get the B number, we take n, which is 7, times the sum of xy, which is 5535, minus the sum of x, which is 605, times the sum of y, which is 62, over the same denominator. What makes this a little easier is that the denominator for the A and the B formulas are the same. So when we calculate that, that comes out as 0.1898. So the equation for y prime is negative 7.5441 plus 0.1898x. Now, another way we could get it instead of calculating it ourselves, is if you have put in the data points, if you'd entered those into the graphing calculator, like I showed you last time, and then you push stat, go to calc, go down to number 8 on the list, linreg, which stands for linear regression, a plus bx. Hit enter a couple times. It shows me that A is negative 7.5440997, and B is 0.18976, and so on. So it gives me the A and the B for the equation. And if you're doing this on Excel, there's more than one way you can ask Excel to give you the equation. One way is described in the book, but the way I like to do is make a scatter plot like we talked about last time. Then while you're on that scatter plot, click on Design, Add Chart Element, Trend Line, go down to More Trend Line Options. Make sure it's selected Linear. See, it's drawn a line, and then if you go down here and check the box next to Display Equation on Chart, it actually makes the equation appear on the chart there. Then if I wanted to, I could change the size of the font or something like that to make it easier to see. Or I could try at least. But there you see the equation they have is y equals, and they put the x term first, which is a different way of writing it, but it's the same equation we got, 0.1898x minus 7.5441. So there it is on the chart. Now that we have this equation, we can use it to answer questions like, find y prime when x is 90 degrees Fahrenheit. That is, we'd be predicting, according to the pattern we've seen, what's our best guess for the number of emergency calls they could expect on a day when the temperature was 90 degrees. So we take our equation, we plug in the number 90 for x, so we're calculating 7.5441 plus 0.1898 times 90, and that comes out to be 9.5379. So around 9.5. So somewhere between 9 and 10 phone calls would be the most likely number for how many calls they would receive on a day when the temperature was 90 degrees. That would do the best job of fitting the pattern. So if you go back to our graph, and you look at the point on that line where the x-coordinate is 90, the y-coordinate of that point on the line is about 9.5. So if there were a point on the line whose x-coordinate is 90, its y-coordinate would be about 9.5. Okay, I'll come back in the next part and work through another example. I've shown you all the basics. We'll just see another example or two.